Hi everyone. So for this session we're going to look at using the Laplace transform to transform the differential equations describing our circuits into the S-domain and solving the circuits and then bringing them back into the T-domain. So just to remind you what we are going to do, the general procedure, we're going to get the ODE describing the circuit using KVL, just as we'd have done before in the first and second order circuits. We'll take our Laplace tables and we'll look up the terms, bring it into an equation in the S domain, right? This is the S domain here, the Laplace domain. We will solve for the voltages and currents that we want, and then we will look them up again, this time going the other way in the table, and get the circuit solution. So let's take the example of an RL circuit, and we have here the voltage source, DC voltage source, and we're going to switch this down. We are assuming 0 initial conditions, and at T0 we close the circuit. We could then write our KVL equation. Here I have RL, but this should really be IL. It doesn't matter, the resistor current, the inductor current is the same current, but here I have IL. So the voltage across the resistor is Ri, and the voltage across the inductor is L di dt. And when we sum those, we get it equal to the source voltage. Of course, you could also do this by just doing your loop equation. So you could say Vs minus Vr minus Vl is equal to 0. It will be exactly the same thing. Now, I have to take this equation into the Laplace domain. So I have my equation, which is Vs is equal to I t by R, and this is the inductor current, plus L di t dt. So I'm going to transform now each one of these terms into the S-domain function. So Vs is a constant. So Vs, if I look up in my tables, I will see that it becomes, if I had K, it becomes K on S. So Vs becomes Vs on S. ILT, if I transform IT, I get IS. And if I transform, so here I have IT and that becomes IS. And then if I transform L di dt, so if I transform the di dt, I could look up in my modified transform tables, and I will see that dn ft dtn, so here these are for arbitrary indices. For di dt, the index is 1. So di dt will be, here will be s to the power 1, is minus s to the power n minus 1, in this case is 0, f of 0, which is in this case I0. So here I have this part, and of course I multiply R by is and L by the transform here because these are just constants. So I end up with my equation now in the Laplace domain. And if I want to solve for the current, then I simply make Is the subject of the formula. So if I collect all the terms in Is, which I'm doing here, and substitute my initial values at t is equal to 0, we said the initial current was 0, so I substitute all those things and I end up with this equation for Is. Now what I have to do is solve for Is by bringing it back into the time domain. So here I make Is the subject of the formula, and then I want to put this Vs on S, Sl plus R. I want to put this in forms that I could find in the Laplace tables. So I'm going to split it into these two terms, and I know what the transforms for these two terms are if I look at the tables. So now that I've split these, my problem is to find the values for A and B. So I'm going to do that by comparing coefficients. And you could go through the mathematics here. This is just recombining them and getting the coefficients of A and B. And I could compare the numerators and I could get what A is and what B is. So then I could rewrite the equation in the Laplace domain like this. This is with my terms separated. And I can take out the Vs on R, since that is common to both of them, and it leaves me with this form. And now what I have to do is, now you'll notice here I have SL. In your Laplace tables, the form is 1 on S plus A. So I have to make the coefficient of S 1. So that is what I'm doing from this step to here. I'm just taking out the S from the L from that step by dividing it by L, putting it on this side of the term here. And then, so I divide by L over L. So you see it becomes 1, and then the L comes down here. And then I could convert it directly into the time domain by looking at my tables. So 1 on S, if I look up that in the time domain, that corresponds to a constant. And the value of the constant is this, which is 1. And then if I have a term of this form, it is e to the minus at. If I have 1 on S plus A, this transforms to e to the minus at. So the R on L here becomes the coefficient of t in the exponent. And you see what we end up with is the charging equation, exactly what the charging equation for the inductor was if we solved it using our differential equations. So here, just to go back through it, you see what we did. We went from here in the time domain into the S domain. Let me take off all the annotations so you can see it a little more clearly. We went from the time domain into the S domain. So after that, what we did, once we were in the S domain, is that we solved for I, which is what we were trying to do in the time domain, but we solved for it in the S domain. And once we got an equation in I, we were able to take that and bring it back. So we put it in forms that we could look up in the table, and then we could bring it back into the time domain, and we get exactly the same result. So just to summarize, this was looking at how we apply the Laplace transform to solving a basic circuit. You could go and you could try it with the capacitors, you could try it with discharging, you could try it with the RLC circuits, and you know you are correct once you get the same answer as you would have gotten, the same general form as you'd have gotten with the transient method. So next time we will look at taking circuits directly into the Laplace domain so that we don't have to go to the differential equations at all.